Hello Chem 1B, this is chapter 17, lecture video 9, and we're going to do an example problem involving a common ion. So let's say we have a saturated solution of calcium hydroxide, right? And we prepare it. The KSP of this is 4.68 times 10 to the negative 6. We want to know what is the molar solubility, not in pure water this time like in the last video, but in a 0.125 molar solution of calcium nitrate. Now, one of the common mistakes students make is they try to do an equilibrium of calcium nitrate. This guy is 100% soluble. There is no equilibrium here. It breaks down 100% into calcium 2 plus and 2NO3 minus. This is due to the solubility rules that you should have some idea about. Basically, you need to know the first two rules, the ones that are always soluble with no exceptions, and nitrate is an anion that is always soluble. So we should know there is no equilibrium here. This thing's always soluble. KSPs are for insoluble or very slightly soluble salts. So the nitrate's really not a deal here, not important, because calcium hydroxide breaks apart into calcium 2 plus, and if we notice in these two cases, we're forming calcium 2 plus. Calcium 2 plus in this case is our common ion, and what this effectively means is that I have an initial concentration of calcium 2 plus in my solution. So my initial for calcium 2 plus is 0.125 because for every one calcium nitrate, I get one calcium 2 plus, making my initial concentration the initial concentration of calcium nitrate for calcium. Now hydroxide is still 0. We didn't add any hydroxide to the system, so that's already 0. And now we just fill in our change, right? So we have plus S plus 2S. We have 0.125 plus S, and we have 2S for our equilibrium concentrations. We can plug this into our KSP expression, right? So we have 2S squared quantity times 1.25 plus S. Now, KSP here is significantly small, and most KSPs are very, very small. So I'm going to say, hey, let's just use the 5% rule. Get rid of the plus S. This means that now I have an equilibrium expression where it's 4.68 times 10 to the negative 6 is equal to 0.25 times 4s squared, right? 2s quantity squared is 4s squared. Well, at this point, I can just, this isn't a quadratic, it's just a regular algebraic expression. We're going to divide both sides by 4 and by 0.25, and then we're going to square root both sides to get s. And our solubility is now 3.06 times 10 to the negative 3. Now, if you remember back from the last lecture video where we calculated the solubility of calcium hydroxide in pure water, that was significantly higher. I believe it was some concentration times 10 to the negative 2. Because we have a common ion present, we see our solubility in this case decreasing. All right, so that's this problem. Let's continue on. We'll do one more example of this. So let's say, okay, what if we're calculating again molar solubility of calcium hydroxide again, same KSP, but this time it's in a solution with a buffered pH of 13.5. Now, the key word here, and it's very important that we realize it, is this buffered. Buffered means that your pH going to POH, going to OH minus concentration, like we did in a past problem here, is not equal to the equilibrium condition. Because buffered means this is not changing. Which means this guy, this pH that we're going to use, that's going to go into our initial. So again, we're still going to do pH to POH to OH minus, but this is your initial OH minus concentration in this case. So if we set up this problem as we've done, we again don't care about that because it's a solid. This guy's 0, and this guy here is what I calculated using this whole process. Which again, I'm not going to show on this slide because we've done it quite a bit but we can go pH, we have it, it's 13.5. 14 minus 13.5 gives me my POH, which is 0.5. I can do 10 to the negative POH to get OH minus concentration, and you should get 0.316. Now we fill it in the rest of the way as usual, plus S plus 2S, S 0.36 or 0.316 plus 2S. We can set that into our equilibrium expression. Again, our KSP is super tiny, 10 to the negative 6. We can definitely use the 5% rule here, so we're just going to get rid of the plus 2S here. This makes the solution pretty simple. We have 4.68 times 10 to the negative 6 is equal to S times 0.316 squared. So we just divide the 0.316 squared over onto the other side, and we can get our solubility, which is 4.7 times 10 to the negative 5. And as you can see, this is the lowest solubility we've calculated for this equilibrium so far. And it's because of the fact that calcium hydroxide is a basic salt. So it's going to be very insoluble in a basic solution, and this is a basic solution. Cool. So, if you have any questions, just shoot me an email. All right, so let's do one last solubility problem before we end this video. What is the solubility of calcium phosphate in pure water if the KSP is 2.07 times 10 to the negative 33? One of the things you guys should be aware of is that KSP values can get insanely small, like this one. Calcium phosphate is just a really insoluble salt. The solubility here we're going to expect to be very low. The first step here, though, is going to be, let's write out our equilibrium expression. We have calcium phosphate on the reactant side. It's in the solid state. It's going to break down into the ions that make up calcium phosphate, which is calcium 2 plus and phosphate 3 minus. Now we need to balance this equation. I know there are 3 calciums here, so I need a 3 in front of the calcium 2 plus, and there are 2 phosphates, so I need a 2 in front of the phosphate. Next, we're going to write out our ice table, right? So I have ICE. I really don't care about the calcium phosphate because it's in the solid state, and we don't care about solids in our ice tables. Initially, since we're in pure water, we have 0 calcium 2 plus and 0 phosphate. Now, our change here, because of this 3, that's very important, right? We have a 3 here, is going to be plus 3S. And over here, we have a 2, so this is going to be plus 2S. And then, plus 0, I get 3S for my calcium and 2S for my phosphate. All right. Now, KSP is going to be equal to the concentration of calcium 2 plus cubed. Again, this cube comes from the 3 here, times the phosphate concentration squared. Again, the squared comes from the balanced chemical equation and the stoichiometry involved. Well, I can just kind of plug these guys in. All right, so I have my KSP already. It's 2.07 times 10 to the negative 33. And that's going to be equal to 3S quantity cubed times 2S quantity squared, which I can simplify, right, a little bit here. 2.07 times 10 to the negative 33, leave that like it is. And on the other side, we get 27S cubed times 4S squared, or 108S to the power of 5. Now, the next part is just we divide both sides by 108. Oh, not 180, 108. And I can, I'm going to rewrite this right here so I can finish solving it. What that gives me is 1.92 times 10 to the negative 35 is equal to s to the power of 5. Now I need to take a fifth root here on both sides to get rid of the exponent of 5. Now there are a couple ways to do this, just so you know. Usually you have to use the symbol that's like the square root, and then it has like a y here or an x, something like that, and it maybe has x under here. This button is really I found very annoying to use personally. But you should figure out how to use it on the calculator you plan on using for this class, because you don't want to not know how to do this on the test. Another way to do it is if you have this button on your calculator, the little triangle hat, that's the exponent button. So for instance, if I wanted to take 3 to the power of something, I would do 3 in my calculator and then do the little arrow. And if I want to take the fifth root of this, there's a way to do this. I would put parentheses and just 1/5. Anything to the power of 1/5 is the same thing as taking the fifth root. So this is how I personally do it when I'm doing calculations. Do whichever way you know how to do. But effectively, we need to take the fifth root of both sides here to get S. This will give me a solubility of 1.14 times 10 to the negative 7 molar. So as you can see, we barely have any calcium phosphate actually dissolving here. And that's how we solve this problem. So here's our answer. If you have any questions, as always, please come to my discussion sessions or email me.